ux. Hold on a second, no. Okay, it's going to be xu, xv, wait a minute, xu, yu, 0, something like this, okay, x, v, y, v, 0. And so when you, in the end, it's going to be this right here. The absolute value is going to be the absolute value of that. It's going to be the length of just this k vector, because when you take your, because there's two zeros here, then the I and the j vector get eliminated. So it's just going to be k times this determinant here. So that's what it's going to end up being, like that. But if you swap these two right here, it's still going to be the same, because it's this times this minus that times that, right? So if you swap those two, oh, wait, this should be y, u, y, v. If you swap those two, then if you swap those two, it's still going to be the same. So that's what the Jacobian is, just this m side part right here. Okay, and so that represents that. Now, let's go back to the polar coordinates for a minute. I wanted to kind of show you how this plays out with polar coordinates. Okay, we've already went through this, so we've already figured out what the Jacobian is. It's just r. And so then that's what you're looking at right here. So the area is that. So let me give you an example that's compared with this right here and that. So over here, we have xy, right? And then let's just do polar coordinates, and we will say, just for example, we'll have r. Let's say that's between 1 and 3, and we have theta is between 0 and pi. Okay, and then so then this is theta, and this is r. We're going to make that r. This is theta, as opposed to u and v. So r takes the place of u in here, and theta takes the place of v. Okay, so if we have this condition right here, then r is going from 1 to 3. Theta is going from 0 to pi. And so what we have is we have this rectangle. This rectangle. Over here, if you do the same thing over here, r is between 1 and 3, and theta is between 0 and pi, what you get is this. You get this kind of, oh, it's like half a donut. I'm hungry now. I want to go get some donuts and milk. Oh, well, maybe after class. Okay. So that's what this, okay, so over here, and this is the transformation. This is this transformation right here. That's doing that transformation right there, which is x is r cosine theta, y is r sine theta. This transformation takes this rectangle to this shape right here. So what happens is, one, you want to integrate over this region. So either that or that. So you're integrating over this region here. Okay. So to do a transformation and find, and instead of integrating over that, and integrate over this region here. Okay, so again, the problem is going to be integrate over this region. So you do a transformation, and you instead of integrating over this, you integrate over that. So this is, in this case, this is a rectangle, which is the easiest thing to integrate over if you're doing a double integral. It's one of the easiest regions to integrate over. This one is not so easy to integrate over. This one right here. If you're going to try to go in X and Y, this is going to be pretty difficult. Okay. And then number 3, you use the Jacobian, or the absolute value of the Jacobian. Okay, and so when you integrate over this region, you're integrating over this region, which is the easier region to integrate over, but you have to multiply by R. Okay, you got to multiply by R. Okay, so that's the idea right there. If you're given a really tough region and you try to look for some kind of transformation that will make it an easier one. Okay, and that's generally kind of hard to do. Okay, so let's move on. That's just a brief example. So number 1 from the exercises, find the Jacobian of this transformation. Okay, so they're given you X and Y. So the Jacobian is, go back again and look at it. It's the partial, you take the partial with respect to X on the top line, the partial with respect to Y on the bottom line. Okay, so what's the partial with respect to X here? Partial of X with respect to U, I'm sorry. Partial of X with respect to U.
2U plus V.
Excellent, 2U plus V. And then partial of X with respect to V?
It's just going to be U.
Yeah, good job. Okay, now we do the same thing with Y. And here we're going to get
9V squared.
Yep. And then here
it's going to 18UV.
18UV. Okay, great. And now we multiply these together. This times this, that's going to give, I'll write it out. And then subtract and multiply these together. That's 9UV squared. Okay, so when we distribute, we get 36U squared V plus 18UV squared, minus 9UV squared. So that's going to be 36U squared V plus 9UV squared. Okay, and that's my final answer. Okay, number 2. Okay, on the first page, we didn't talk about triple integrals. We're integrating over a solid instead of integrating over a 2-dimensional area. But it pretty much plays out the same way. The Jacobian is going to be, so this is the Jacobian UVW this time. And this is just going to be a 3×3 determinant, or the determinant of a 3×3 matrix. So you focus on the X first, and you take the partial with respect to U, which is going to be 0 here. And then with respect to V, you get a 9, and then W is 18W. Okay, then this one, with respect to U, this is going to be 14U. With respect to V, it's 0, and with respect to W, it's 7. And then here, this is going to be 3, 6V, and 0. Kind of a waste of 0. It would be better if that 0 was right here. Oh well. So anyways, let's take this determinant. And this right here represents, I forget the name of it. I forget the name of this, but it represents the volume of the parallelepiped. Okay. So anyways, come down here, that's 0. And then this one gives you, whoa, that's a pretty big number. Um, 189. Okay, then these three, I got my calculator. Okay, so 18 times 14 times 6. Whoa. Whoa. So that's 1512 UVW. Okay, then going back the other way, you have 0. Oh, it's all zeros back the other way. Okay, great. So 189 plus 1512 UVW.
Hey, Brother Hurst, I'm kind of confused how you got those numbers coming out of the matrix.
These numbers here?
The ones right before it.
Right here?
Yeah, the first one makes sense. Yeah, the other one to the left. Those ones.
Oh, I just copied down the first 2 columns.
Oh, okay. Then you're doing the, oh, that's what you did.
I'm just doing the determinant, sorry.
Right. Okay, that makes more sense now.
So it's, yeah, so it's, okay. Okay, great. So let's move on. Number 3. So find the image of the set S under the given transformation. S is the square bounded by the lines U equals 0, U equals 1, V equals 0, and V equals 1. Okay, so let me go ahead and draw what that looks like. So if this is the UV plane, then U equals 0 would be this right here. And U equals, wait, I'm sorry, U equals 0 would be right here, I'm sorry. And U equals 1 would be over here at 1. And V equals 0 would be here, and V equals 1 would be up here at 1. Okay, so this is the region right here. Okay, so what we're going to do is I'm going to say, okay, so U equals 0 is this part right here. Okay, that's U equals 0. Now, if we take U equals 0 and we plug it into here, then we have X equals V, Y equals, okay, we have Y equals this. But I'm plugging U equals 0, that means that's going to be a 0. So you have X equals V and Y equals 0. Okay, so anywhere, in other words, X could be anything, but Y has to be 0. Okay, so let's say that's Y, this is X. So that means that this is going to be here. It's going to be this horizontal line here, because X can be anything. X can be anything, whatever value V is, but Y has to be 0. So it's this horizontal line. Now, if I go from here to here, then V has to go from 0 to 1. So this is really going from 0 to 1. Okay, now let's do this one right here next. This top part. Okay, this is X equals, no, It's y equals 1, right? Y equals 1. No, I'm sorry. Not y equals 1. It's v equals 1. What am I saying? Okay, that's v equals 1, right? Okay, so now, if we say v equals 1, and we plug that into here and here, then we're going to get x equals 1, y equals 2u. Okay, so plugging a 1 in for v here and a 1 in there, we get x equals 1 and y equals 2u. Okay, so that means that, and then u goes from 0 to 1, right? So if u equals 0, we get 1, 0. And if u equals 1, we get 1, 2. Okay, so 1, 0 is here, and then if u is 1, we have 1, 2. So this is let's, dang it. Okay, let's do this. Erase that. Okay, let's say that's 1, and that's 2. Okay, 2. Okay, so then we have a point right there. So that basically this right here is going to be this vertical line segment from there to there. Okay, now, let's see here. We can use purple. Okay, let's do this one next. Okay, goes from, this is u equals 1. Okay, so if we plug u equals 1 into here, then we get x equals v, and then we get y equals, well, plugging a 1 in for u just makes this 1 plus v squared. Okay. So x is v, and y is 1 plus v squared. So what you can do is you can take this and plug it in, plug in an x for that. So you have y equals 1 plus x squared. And then here we have v is 0, right? V equals 0 is going to give you 0, 1. It's going to give you this point here. And then over here, of course, you're going to get this point. And so this is a parabola. This is the part of the parabola that goes up like that. Okay, so this image is that piece. And then if you do the other one, then you're just going to get this right here, by the way, if you do the other one. So this region maps to this one right here. So this is what the image is going to look like, which is the bottom right answer, okay? The bottom right answer. Okay, so let's look at number 4. The region R is bounded by y equals 2x minus 5, 2x plus 5. This is 2x plus 5 right here, right? And this right here is y equals 2x minus 5. And then y equals 5 minus x and 7 minus x. Okay, so this is y equals 5 minus x, and this is y equals 7 minus x. Okay, find an equation for a transformation T that maps a rectangular region S, and I guess they're putting this S out there for you, where the sides of S are parallel to the x and v axes as shown in the figure. Okay. So, where to start here? Okay, so over here, over in this one, this is bounded by v equals 5. This is v equals 7. This is u equals -5, and this is u equals 5. Okay, so each of these has to map to one of these sides over here. Now, this is a 5. There's a 5 and a 7 there. So, and there's a 5 and a 7 there that appear. And then there's a -5 and a 5, and so -5 and a 5. So that's pretty much this one's going to have to correspond with this, and this one's going to have to correspond with that one, and so on. Okay, so this, and then this is going to correspond with that one. And then this one is going to correspond with this one, okay? So, so let me try to summarize that right there. So this u equals -5, that's going to have to transform to, I said this one right here, y equals 2x minus 5, right? And this one, v equals 7, that's going to have to go to y equals 7 minus x. And then this u equals 5, that's going to have to go to this, wait, yeah, this one here, y equals 2x plus 5. And then, what's the last one? Okay, v equals 5, that's going to have to go to y equals 5 minus x. Okay, now, here's what you do. If you take this right here and you manipulate it, bring this 2x over here, and then do the same thing with this one. Well, do the same thing with all of them. I guess that I could have written that as, hold on, let me write it as x plus y. And then brought this over as x plus y equals 5. Okay, so as you can see here, you have u equals -5, and here we have this equals -5. We have u equals 5, we have this equals 5. So those are the u's. So u should be -2x plus y in the transformation. Okay, and then we have v equals 7 and we have this equals 7. We have v equals 5 and we have this equals 5. So v is x plus y. Okay, now you can put those, I think it will accept these as the answers. And this, because this totally defines the transformation. It'll accept those as the answers. Now, if you want to calculate the Jacobian, you're going to have to solve for x and y though. So, and it turns out that
work, Brother Hurst.
What's that?
Those answers work.
Yeah, those answers work. I'm just saying if you want to find the Jacobian, then you'll have to solve for x and y. And I think you could probably figure out how to do that. But anyways, here's what you get. V minus u over 3. And y is 2/3 v plus u over 3. I guess I should have put the u's in front of the v's, but oh well. Okay, so yeah, so that would also work if you put those answers in. And then from here you could actually calculate the Jacobian. Okay. Although it just occurred to me that I think the Jacobian is, you could calculate it this way with these ones and just take the 1 over that or something. But I have to look into that. Yeah, I'm pretty sure. Yeah. Okay, so let's move on to number 5. And here we're actually supposed to evaluate an integral. And R is the region bounded by the ellipse. And we're supposed to use this transformation here. Okay. So one of the first things we can do is find the Jacobian. Okay, so the top row is going to be what? Does anybody remember?
Yes. Oh, partial of x?
Yes, the partial is with respect to x, which partial of x is respect to 2.
Oh.
It's going to be 2.
You.
Never mind.
And this one, 0. Okay, over here, you're going to get 0, because there's no u's here. And then
And 5.
partially and 5. Okay, so that's just going to be 10. And the absolute value, that's 10, so 10 is going to be what we're going to do. Okay, so now we're ready to set the integral up. And let's see, we also have to figure out what happens to the region. Okay, so let's see here. If we make x equal to 2u, then that's going to give us 25 times 2u quantity squared plus 4 times 5v quantity squared equals 100. Okay, so that's 100 u squared plus 100. V squared equals 100. So that's u squared plus v squared equals 1. So let me just write, so it's bounded by that ellipse. So let's call this S. Okay, so S is bounded by the circle. Okay. Okay, so S is bounded by the circle. Okay, now, so what are we integrating? We're going to be integrating 10. We have this 10 here. The x is 2u, so that's going to be 2u squared right there. And the dA, we need to get this thing into play, so that's 10. Okay, so 10 du dv. Okay, so it's essentially a quick picture of this would be, here's your circle right here, and this is your S region, this is S, and this transformation is maps that circle to this ellipse right here, which, dang, what is this? This is x squared over 2 squared plus y squared over 5 squared equals 1. So in the x direction, it's going to go out 2, and then it's going to go 5 in the y direction, like that. And so we have an ellipse, like that. And you can kind of see why, 10 is the factor, because here is a much bigger region, and here you're only integrating over this. So to make up for this, and this is the integral that you want to find the integral over this big region, right? And so if you're taking the integral over a smaller one, then you're going to have to be, that's why the 10 comes into play. Okay, so now, of course, at this point, you're integrating over inside of a circle, right? So you're going to just switch to polar coordinates. I guess we could have done polar coordinates from the beginning, and you know that to get the circle, you have r is going to go between 0 and 1, and theta is going to go from 0 to 2 pi. That gives you the whole circle. And so this is going to be, let's see, 400. So that, and that is 400. And then u kind of takes the place of x. So that's going to be r cosine theta, all squared. And then there's another r dr d theta. Hold on. Okay, so I decided I want to borrow this 4 here for a minute. Because this is r cubed, and then we have cosine squared theta, dr d theta. And this becomes r to the 4th from 0 to 1. That is just 1, so it just kind of goes away. And this one is, this integral is 1/2 theta plus a 4th sine of 2 theta. And theta goes from 0 to 2 pi. So that goes away. And then this one's just going to be, whoa, 100 pi. 100 pi's, whoa, yes. This calls for 100, this normally would call for 100 pi celebration, but because of the quarantining stuff that we're supposed to be doing, then we can't do it. Okay. Yeah, that's right. Okay, so number 6, evaluate this integral 10x y dA, where R is the region in the first quadrant bounded by the lines y equals 2/3 x and y equals 3x, and by the hyperbolas, whoa, by these hyperbolas. And you're supposed to use these transformations. Wait, these transformations here. X is u over v and y is v. So if you plug these in, so plug a v in for y, that's going to be v. And then for x, you're going to plug in u over v. So this is going to be 2/3 u over v, which gives you v squared equals 2/3 u. Okay, let me come down here and try to draw what that looks like. Okay, so think of this as y squared equals 2/3 x. And that's going to be a parabola that opens up this way. Okay, so that's v equals v squared is 2/3 u. That's that first one. Okay, so now let's use a different color, and we'll go for this one. Okay, so this is gonna be v. So y is v, and then x again is u over v. So you're gonna have the same thing. So v squared equals 3u. Okay, this is a parabola that opens up this way, but it goes higher. Okay, like that. Okay, now this one right here, you have xy equals 2/3. So x is u over v, y is v. Oh, so good. So you get u equals 2/3. Okay, so if you put, let's put 2/3 right here. And now it's going to be this. So u is 2/3. That means that's a vertical line right here, right? And then the last one, this one right here, you're going to get u equals 3. So come over to 3. And we have u equals 3. Okay, so great. So this is the region that we want. Let's calculate the Jacobian. Okay, so just based on this right here, we calculate Jacobian. So what goes in the top here? The partial of x with respect to u is first, right? And what's that?
1 over v.
Yes, it's 1 over v. Great. And then the partial of x with respect to y? That's going to be negative v squared. Okay, great. Now, partial of y, so here's y. With respect to u, that's going to be 0. And then this is 1. So that's 1 over v. Now, here, v, in this region, v is always positive. So the absolute value is also that. Okay, so that's all we need. 1 over. So we just need the 1 over v for the Jacobian. Okay, so now we're ready to go ahead and calculate the integral. And what we want to do is we want to integrate over this region here. And what we need to do is solve for v, because it's better if we integrate in v first and go from this boundary to that boundary. Wait, square root of u. Square root of 3u. Okay, so upper line is the square root of 3u, like that. And then the same thing with this lower bound. V equals the square root of 2/3 u. The u is under the square root sign too. Okay, and then what are the limits on u? And it's going to go from this line here, 2/3, up to 3 on u. Okay, so this is integrating in v first, and then in u. Okay, and this part right here, we have a 10. I'll pull the 10 all the way out here. Okay, so this 10 I pulled it all the way to there. The xy, we already know that if you take xy, that's going to be u. Okay, so that's your xy from here. And then we have the Jacobian, right? Okay, that's your Jacobian. Or absolute value of the Jacobian. But I'm just putting it like that because we know that v is positive, so absolute value is just going to be 1 over v. Okay, great. So now we can go ahead and focus on integrating this. So we still have that. And integrate with respect to v, you're going to get the log of v, right? And that's going to go from v equals the square root of 2/3 u up to the square root of 3u du. Okay, that, and then we're going to have u times the log of this. Now let me do a little thing right here. So the log of the square root of 3u, that's the same as 1/2 the log of 3u. Okay? And likewise, this is 1/2 the log of 2/3 u. Okay. Okay, so we have this 10 here. And then what happens is right here, all of this, of that, you can factor a 1/2 out, and you're going to have log of this minus log of that, which is the same as log of 3u divided by 2/3 u. Okay, and so the u's miraculously cancel out, and what you end up with is simply u over 2 times the natural log of 9/2. Okay, so it looked like, so it's like you have u times log of 3u, so it looks like, oh, not again, we have to try to integrate that kind of thing. But because we have this minus right here, and then the u's just cancel out, and so we use log of 9/2, which is just a constant, so that's great. Okay, so if we take this 10, we take this 10 over to log of 9/2. We take all of this stuff out except the u. You integrate that, you're going to get u squared over 2 from 2/3 to 3. Ten tabs is 5. And this is going to be 9/2 minus, is that 4/9 over, dang, over 2. Okay, if you put that in the calculator, you're gonna get 385/18 log of 9/2.